So today we're going to final exam. I haven't heard anything about the final exam date. We asked; they're looking into it. Apparently, um, I will keep asking because it looks like they changed it twice, and so I assume it was because of conflicts with other people, and they're looking to try and move that thing around. But it's it'd be good to know, right? Like I kind of want to know, and I'm sure you guys really want to know, so you can plan. I think no, I didn't post anything new because we're continuing from what it is. It's just keep writing stuff, so there's no new slides or anything. But I think I posted what we did up to last class available. It's actually just going to update the file. So last class we ended by discussing this guy. We're saying we don't get this. We get this. If we add iodine chloride across double bond. And so we discussed that, okay, so we're looking at this kind of thing. It's exactly like adding hydrogen chloride, sort of. You show the bond polarization. You figure out which one's going to be attacked. Very, very aggressive language. Which one's going to be attacked by the lone pair that are on double bond, or the double bond, if you want to think of it that way. I think of it as the double bond, but it depends which way you think of it from the previous slide when we were discussing that. And then you figure out which side it goes to, and we discussed that, and we went, okay, so it's not going to put the positive charge next to the CF3 because the CF3 is electron withdrawing. We don't want plus next to plus, so we're going to avoid that. And now, when in the previous examples with hydrogen, we were showing it was a flat p orbital, and so you can equally attack from the bottom or the top. And now I'm saying you can't do that. You only get attacked from the bottom. You do not get attacked from the top. So what's going on there? Well, what's going on there is, let's just think about the double bond again. So it's double bond, right? Single bond, double bond. And let's say we are attacked. I'm just going to draw in some methyl group, slightly different molecule, I think, than what we had, but it doesn't matter. And let's say, again, we have this ICl. Again, we've decided that it's polarized. Now, let's do the attack. So we attack with double bond, attacks the iodine, breaks the iodine chloride bond. In this case, you know what? I'm going to draw exactly the same thing we had. I'm just going to make sure I put it in there. It's got a CF3 on one side. So one way we can draw this, I'm just going to draw it like here, and just bear with me for a moment. Maybe you'll agree. You're now making a new bond with the iodine. And the iodine, as we know, has 3 lone pairs on it. And I just gave up electron, the iodine chloride bonds to the chloride, and we have Cl minus. And over here, we've got that empty p orbital, which is positively charged because it is empty. So that's absolutely equivalent. What I've drawn there is absolutely equivalent to me drawing that, which we agreed was that. I think I've drawn the enantiomer, but that's okay. Okay, now, if we're thinking about that, I've got this big empty p orbital, positively charged, does not have its full octet, and it's awfully close to an sp3 orbital from this iodine. I got electrons. I got something that wants electrons. Let's solve that problem. Got to bend the angle a bit. This is not a happy angle. We've got 2 electrons in each of those. And now the iodine is making a bond to that carbon. That's a 3-membered ring, everything sp3 hybridized. That's exactly the same geometry as a cyclopropane. Positive charge is now on the iodine. If we draw it like this, what am I doing? Using a lone pair on the iodine to attack the carbon. And now the iodine is kind of making a bond to both of those, and it is formally positively charged. Now, if we think about that, and we compare those two structures, it's better to have the positive charge on the iodine because everybody has their full octet. These aren't resonance structures. We've moved atoms. But what we've kind of done is a reaction where we bound the iodine to one of them, and now it's also bound to the other one. Now, hydrogen can't do that because hydrogen only has one orbital because it is 1s. Iodine has these extra orbitals, so iodine can do this. So can oxygen, so can bromine, so can chlorine, so can anything that isn't hydrogen. So now, when we think that this is how this thing exists, we have our chloride coming in, and it can't come from the top because the iodine is in the way. In fact, what it needs to do, if you're thinking about this from what we've drawn over here, is the chlorine needs to interact with this antibonding orbital. Of course, the antibonding orbital, I'd have to draw a new one. I'm not going to right now, but it's going to be directly in line with this little nub here. So chlorine needs to come in from the back side behind the carbon atom. And it displaces the iodine. Okay. So that explains why chlorine and iodine are on the backside of each other. Doesn't explain why the chlorine attacked that carbon and not the other carbon. But that's explained by thinking about this for a second. So we have a structure here where the iodine is positively charged, formally positively charged. It just donated some electrons to make a new carbon-iodine bond. And you can think of, well, it's kind of donating into both this one and this one. Right? One of those is kind of it's got 4 bonds, like 2 bonds. I guess they're both covalent, but they're both kind of weak because they're kind of like spring-loaded. They're ready to open, both because it's a 3-membered ring, which is bad, and because the iodine is formally positive, which is bad. Is just my microphone shitty, Nulia? See if I can turn it up. See if that helps. Okay. Okay. Like, I'm not in a great mood, but that's neither here nor there. So, if we're thinking about that, then depending who you talk to, they will disagree with me on this. You can think about this as resonance or equilibrium. No one is going to disagree on equilibrium. I kind of think of this as resonance. But let's just think that this system, instead of being quite only that, It's kind of a fast equilibrium. And I'll tell you why I think of it as resonance. I don't think it really matters. Sort of a fast equilibrium between these three structures. You know, the iodine is positive, doesn't want to be positive, it's making two bonds, doesn't want to make two bonds. Okay, it breaks one of them. That makes that carbon positive, it breaks that one. That carbon doesn't want to be positive, reforms back to this. It can break the other one, make this carbon positive. And altogether, if we're thinking about this whole molecule, what we can kind of think about is there's kind of like a hybrid structure. Now, again, you could replace those equilibrium arrows I just drew there with resonance arrows. And it's sigma bond resonance, not pi bond resonance, which is all the resonance we've been doing, so I'm a little nervous about talking about it. But the idea is that we're just moving electrons. No, the atoms are moving. We're just moving electrons, and we're trying to stabilize this charge. And so if we do that, we can kind of think of what this molecule looks like. Is there's quite a big positive charge in the iodine. There's a decent sized positive charge on that carbon, and there's a very small one on that carbon, because this is really unstable, because it puts the carbon positive charge next to the CF3, which is bad. We don't want the positive next to the CF3. So if the molecule can switch between these two guys, it wants to spend most of its time like this, out of these two, because the positive charge is next to the CF3. So more of the positive charge character of this molecule is on that carbon. This seems to look a lot like a resonance hybrid, but it's kind of like we're discussing the charge density of an equilibrium system, or you can say it's the charge density of the resonance hybrid. I'm fine with either explanation, but it's not. There are people who would say that's not resonance because you're breaking single bonds. I see that argument. I think it depends what you want. On the C at the top is actually a delta. These should all be deltas. And they're all delta positive. No, they're all delta positive. All of these are positives. There's no delta negative here because the chlorine has the negative charge. But what we're doing here is we're looking at these guys and we're thinking, that's the bigger positive charge. So the chlorine, when it comes in, is going to attack the biggest positive charge. So that's going to be that carbon. The iodine's also pretty big. If the chlorine attacks the iodine, we just go all the way back to starting materials and remake the double bond. That's fully possible. Might even be the most likely thing to happen, but nothing happens that way. Yep. That's exactly it. So the chlorine attacks the biggest positive. And that makes it the most reactive center. It's kind of like magnetically attracting the negative charge, right? Because the bigger positive. Yeah, and it does. It can attack the other carbon. We're going to pretend that you only get one product out of these reactions. You don't. You get multiple products out of all these reactions, but you get one major product. And I'll try and frame questions always as the major product. So yeah, it is possible it can attack the other carbon. You'll probably, with this molecule with the CF3 there, magically disappear.
He's doing it so messy. Because
Just gonna mute someone. Oh, they muted themselves. That's all good. Okay. Depending what else is there, you can actually get kind of good ratios. I'd expect this one to be like 9:9 to 1. That CF3 really doesn't want a positive charge next to it. But for other kind of systems, you can also get like sort of 2:1, 3:1 mixtures. We're just going to worry about I just threw my pen across the room. We're just going to worry about the more, the major ones. So this is the difference between any other atom and hydrogen when they get added like this. So let's look at almost a simpler example. So we take a step back. Okay, we're going to take a step back and a step forward. I don't know. Sure. So we're going to do this in the dark, and we'll talk about why that's important in a much later lecture, but I'm just going to mention it's in the dark. So if we add bromine, Br2, across double bond. Now, in this case, that bond isn't polarized, right? You got two bromines on each side. But at any one moment, the bond is polarized. Dipoles induce. And so I am arbitrarily going to attack the bromine that is more convenient for me. So I'm going to skip ahead right to that three-membered ring that we drew. Oh, Gabriella, I'll come back to that, Gabriella. You know what's the biggest positive because it's the most stable positive. So in this case, we're going to have the same kind of example here. Plus Br minus. So if we think about the same kind of analysis for this kind of system, if I asked you what is the intermediate of this reaction, you would draw me that. So if we're thinking about this kind of thing, we're thinking, okay, that's cool. What happens next? Where does the bromine go? I know that what I should be looking at then what if I move the positive charge onto the carbons? So what I'm comparing in my mind or on paper, whatever works for you, are those two guys. Because those are the two options. I can break either one of those carbon-bromine bonds, and what I want to look at is where is the positive charge on the carbon? Which of those carbons wants the positive charge more? And so I walk through my things. I don't see any resonance. The induction looks about the same. I don't see any like fluorines nearby or other atoms. Like there's a bromine nearby, but they both have the bromine nearby, and it kind of cancels each other out. It's all in carbon. And so I'm coming down to this whole hyperconjugation. And so again, if we're thinking about that, this guy is a tertiary center. This guy is a secondary carbocation. Tertiary carbocations are more stable than secondary carbocations because there's more opportunities for hyperconjugation. So if I'm thinking about this molecule, I'm already kind of sketching in my mind, oh yeah, of course, at the university, it doesn't let me do this. I've got a nice big delta plus there, and a much smaller delta plus on that one. And that's because, again, hyperconjugation, the tertiary is more stable than the secondary. So if you have to divide charge between them, the tertiary is going to hold more of the charge. So our nucleophile comes in. I was thinking about so the nice thing about curvy arrows is as long you can draw them curling anywhere you like. Take them on a vacation around the page, as long as they start and end in the right place. I was thinking about coming in at a different angle, but I'll come in there. And so I'm going to come in from behind the bromine. When I do that, The bromine pops open on the other side here. I'm going to push the methyl group that was down is going to be pushed into the up position. And our new bromine is going to be on the bottom. No, so Bavian asked, it would be okay if I put the bromine into the page. Nope, you could do that. That's equally correct. And then the methyl group would be up. You're gonna get the enantiomer of this, and that's perfectly fine. I just always like drawing things out of the page. I really hate drawing things into the page, so I always prefer to draw them out if I have an option. So this holds true for basically any of these kinds of systems. We're gonna do one more example that's very similar to these ones, and then we're gonna jump to another. Well, it's actually still very, very similar to these ones because there's just not that many patterns. So let's think about so this is bleach, and this is actually one of the ways that bleach kills stuff. Because what it does is it basically oxidizes the double bonds in a lot of bacteria cell membranes, and it breaks them down and kills them. We're going to come back to why it's in the dark. Because if it's in the light, you get something different. And it's because you follow a different mechanism. And we're going to come back to that at the end of the class. Like course, really. Okay. So what I'm going to do here is I'm going to introduce the concept of equivalence. I'm going to say one equivalent and one equivalent. So an equivalent is a mole equivalent. So I can say there's one molecule of each in the flask, or there's 1,000 molecules of each, or there's 10 to the 23 molecules of each. But it's a 1-to-1 ratio of the two. It says equivalent. Equiv. Which is short for equivalent. Which is kind of a stoichiometric molar ratio. Which is a jargony way of saying you have the same number of things of each when you count them. So you got one of them, and that's what you got. So the question is, okay, react these two guys together. Well then, we've got a few things we need to think about here. No, did not want to do what I just did. Problem is I clicked too quickly with this thing. We have to think about, this means heat. I'm sorry, if you haven't seen the triangle, the delta, it means heat. And heat is arbitrary. It's enough. Sometimes heat is 0 degrees, sometimes heat is 10,000 degrees. We're just saying there's enough heat to get this to go. It's probably about 40 degrees or so. So we have two double bonds, and we only have one of these. So we're going to react one of the double bonds and not the other. We've got Andrew saying the top double bond. Any other opinions? Then I'll ask why. I can see the glossy eyes through the Zoom portals that are just your names on the page. Okay, Andrew, do you want to? Yeah, exactly. Okay, Keith and Andrew are both right. Let's just think about what you would get. And we know this how this is going to go because we've been drawing these. We're going to attach a thing to one end of a double bond. That's what's going to happen. So let's think about our options. I can basically write that as E nuke, where this is the electrophile, this is the nucleophile. It's followed the patterns for everything we've seen so far. This is positive, that's negative. That bond wants to break towards the negative, like delta positive, delta negative, I guess I should say. This is kind of like a general rule, and we can think this thing through. And it doesn't matter what's what. That's all detail. Who cares? So we're going to attack the E plus, and we're going to displace the nuke minus. In our previous case, they were both bromine. In one of our other cases, E plus was H, the nuke was Cl. That was HCl. Okay. Now, if we do that, we have two choices. We can put it there. Or we can put it there. That's a positive charge. That's really poorly drawn. From comparing those guys, I'm thinking, okay, I really don't like primary carbocations. They make me feel kind of nauseous in my belly. I just had a big piece of cake, so that's probably a bad idea. I like tertiary carbocations, but even more than tertiary carbocations, I get really excited about the idea of resonance. And we've got resonance here. So we have resonance. Resonance is awesome. Now, I want to draw the resonance structures because I'm looking for a trick. I'm looking, if I add to this top double bond, is this really the site where I'm going to get attack? Is this really where I have the more stable positive carbocation? And I have to consider and if there's resonance, I have to consider the other one. And the other one is down here, and it's a primary carbocation, and that sucks. They have the same resonance. You wouldn't keep the positive on a terminal. Terminal's bad. But resonance is good. That's like one structure, right? But we're just considering our options. Now, what if we attack the bottom double bond with that? Okay, that's one option. That's a bad option. I do not like that option. Again, primary carbocation, it's stuck there. That's my other option. And I've got resonance, and I like resonance. But this resonance isn't as good as that. The best this guy can do is a secondary carbocation. The best the top one can do is a tertiary carbocation. Otherwise, they're very, very similar. You don't have any other real effects going on. You have this resonance comparison. That is the better one. So we've looked at these ones. We're going, okay, I like this the most of the four places I could put this electrophile. Now, there's two options within that. I could either attack that carbon or I could attack that carbon. And it's coming back to exactly what we've just been discussing, which is where is most of that positive charge going to be sitting? Well, most of it's going to be sitting on this guy because that's tertiary. So I'm going to expect an attack there. So this analysis down here is me pulling apart the double bond system and going, what we're going to add when we do our chemistry. We're going to make that. Now it doesn't help me figure out what the electrophile is, because now I got an OHCl bond. In which way is that polarized? And for that, I reach out to my handy periodic table. I'm looking one up online with electronegativities. It's a real shame. I don't think our textbook has one on the inside covers. And I found some shitty old periodic table that's really low resolution. You know, looking up electronegativities online is something you can definitely allow to. Okay, well, here's one. I'm not sharing the screen, but what I'm reading there is oxygen is 3.5, chlorine is 3.0. Oxygen is more electronegative than chlorine. That's the way the bond is polarized. And I'm thankful that's because I hadn't checked the numbers before. I know which way it goes. I'm really glad that the electronegativities line up. So our E is the positive thing of that bond, which is the chlorine. Go back. And we figure out which way this one's a really tough one. I always think this one's the one I always need to, double check myself because I always forget which way it goes with bleach. Luckily, you check it by looking at the electronegativities, and luckily, on any evaluation you're ever going to need to do for this class, you're going to have the electronegativities in front of you because you can have anything you like. So we break that bond. And we have a chloride, and we have the OH minus. Now, as we've been discussing, that's not really how this sits. This goes immediately to chlorine closing up on this. Making that 3-membered ring, because chlorine is not hydrogen, so it's got the orbital, so it does it. But now we know that the bigger because we've already done this analysis when we were figuring out which word to attach to chlorine. We know that the bigger positive charge, because it hasn't changed, because all the same features that we were worried about earlier, and nope, now it's zoomed in. I don't want to do that. I don't know what happened. Stop it. I just have to be patient. I have to press. I have to wait for everything to get smaller. Then I have to click. And patience is my weak suit. We know that this is the bigger positive, because we've just spent 5 minutes figuring that out, and that hasn't changed. Now there's a chlorine snapped onto it, but who cares? It's the same, because we have a chlorine snapped onto the other one too, so it's all equal. So at this point now, OH minus comes in from the back, breaks the carbon-chlorine bond, and if the OH came in from the back, it means the methyl group that had previously been there got pushed up. And so we get this product. So, what have we learned? We learned that these things come in opposite to each other. You get trans, and the nucleophile goes to carbon, that makes the more stable positive charge. This is called Markovnikov's rule. Modern variation. Because the old variation is really inaccurate. Yeah, that's CH3. Yeah. That's a good question. Would the double bond ever attack the H in the OH? It's in this case, no, and it's because that OH-Cl bond is weaker than the H-OH bond, HO bond. You can kind of think of it as OHCl is a worse acid than water, so it's unfavorable to do that. Most of the time, we're not going to have anything quite this obscure. I find this one is quite challenging. Now, the halogens are nice and straightforward. This bleach thing is weird and slightly confusing. Okay. Now, there's something we can do if we make that. So let's say, this is true. What we have here, whether we're attacking HCl, BR, IBR, OHCl, doesn't matter. It's the same thing. You get this Markovnikov addition across double bond. So one that we haven't really spent much time thinking, we drew one example, but let's do it again, just with a slightly more complex case. Not more complex than what we just drew, but just let's take this. And we'll sort of take a general version. So we'll do this. So acid in water. I'm not even defining what the acid is. I don't care what the acid is. It's an acid catalyst. HCl, H2SO4, HBr. Doesn't matter, because all it is H plus is our electrophile and water is our nucleophile. Because what we really have, whatever that was, we have hydronium. And it doesn't matter what the other species is. So this is basically a Markovnikov addition of water across double bond. So I'm looking at this guy and I'm thinking, okay. Actually, you know what? I'll give you guys 30 seconds or a minute. Try and predict which carbocation you make. Remember, this is H, so it doesn't do the three-membered thing. And then I guess what the product is once you've got that. Draw some arrows. Yeah, that's OME, like methoxide. Same thing as OCH3. Sorry, if you haven't seen ME, it's methyl. Like, I don't think it saves you many brushstrokes from writing CH3, but still. Okay. It is confusing. That's fair. Do problems. I'm going to put up more assignments this afternoon on this kind of stuff. And all I can say is if this is confusing for you, you have to practice it. Hoping it goes away is how you do badly in this course, because it doesn't go away. Yeah, just do problems. Okay, I've got two options. Put the H on this carbon and a positive charge here, or so let's think about those two positive charges. I like one of those a whole lot more than I like the other one. I'm hoping you guys agree. Good job, Andrew. Okay, so if we're just comparing them, just think about the stability of those charges. This is a primary carbocation. Adjacent to a carbon that has an electronegative thing on it, so we know that the oxygen is pulling electron density out, so this guy's slightly positive. Because that's what oxygen does. It's like fluorine, just not as much, right? Fluorine would be pulling electrons from that carbon. Oxygen does too, just not as much. That's bad. It's a primary next to a partially positive center. That's like a disgusting. You know what I want? I want to be like showing like projectile vomiting. I don't know. It's a very bad carbocation. This guy, on the other hand, is secondary, which isn't great. I'm not excited about secondary, but that's not what's got me excited. What's got me excited, of course, is resonance, because that's the only thing that really gets me excited anymore. Look at that. Isn't that beautiful? I do have really skewed views of beauty. I think the Mona Lisa would look so much better if she was wearing lab safety glasses. Okay, so we have this much more stable carbocation. We have a much less stable carbocation. I know where I'm putting that hydrogen. That's the first step. That's what decides what happens, is where does the carbocation go? I guess it's where the hydrogen goes, because it determines where the carbocation goes. But it's more that where the more stable carbocation is determines where the hydrogen goes. This guy's really happy he is not projectile vomiting. So, which is actually a good reason to be happy. If we've got this, I'm just going to draw the resonance structure again. We have a water nucleophile. We got tons of water. That's going to come in and attack the carbocation. Yes. Thank you. That I completely agree with 3 Budriahi that resonance takes a higher priority than hyperconjugation. I'm going to put the order in, I think, next before we go any further. So we got that. That's correct. We're not done because we still have this extra hydrogen on there. So we need something that can take the hydrogen off. And things that take hydrogens off of things are called bases. And the only base we have is water. Or a little base pore here. So I'm going to use water to strip off that hydrogen. Shitty place to draw that line. And I'm still going to just keep track of the hydrogen we added. So we just follow this principle. Again, hopefully you're seeing the pattern here. First thing we need to do is identify where am I going to put the more stable carbocation. Then I need to identify what am I attacking. This was easy, it was H plus. With the bleach, it was harder. With the BRBR, it didn't matter, right? Then I got to do it. Then, if the electrophile is not hydrogen, it can make a three-membered ring. And that matters not because it changes the selectivity of which carbon is attacked, but it changes which face is attacked because it blocks one face. If it's hydrogen, you get a 50-50 mixture of attack from both sides of that p orbital. But if it's not hydrogen, you always attack from the backside. Then I get my product. Okay, so what do I care about? Still atom is number one. Now, normally irrelevant. Is mostly carbon. We're talking about carbon-carbon double bonds in this thing. I want you to keep this in mind that we're not changing the rules suddenly from acid basis list. Charge stability is still the same thing. It's just that carbon-carbon double bonds tend to involve carbon because they're carbon-carbon double bonds. So your atom that's going to have a positive charge is generally a carbon. And this is where resonance helps. Resonance is your most stabilizing thing for a positive charge. If you got resonance, you don't have problems. 3 is kind of a bit of a tie between induction and hyperconjugation. And you're like, seriously? A fucking tie? That's what I needed. I get it. I agree. I think where I'm going to go with that is, so one example would be this guy. Hyperconjugation says this site. Induction says this site. Induction wins. Because that's a really strong induction group. But not always. Because reality sucks. Same thing. Hyperconjugation wins. Because the induction is a lot weaker. So my promise to you for the evaluations is you're not going to have a case where you have anything reasonable that you need to distinguish between hyperconjugation and induction. Like you have a case like this where they're that's kind of unfair. Now, what would be fair is if I drew that and then I drew CF3 over here. That's a weak inductive effect. If you can't figure out that the hyperconjugation is stronger, then you've got bigger problems. So I promise not to give you something like the first example because that's just it's asking you a little bit unfair. Okay, Claire's asking me to go back for a second. Sorry, Claire. Yeah. And so that's it. Like atom is, electronegativity, size of the atom, both of those components. It depends if you're going across or down a column. Resonance is resonance, which is, resonance. And 3 is induction hyperconjugation. In general, hyperconjugation tends to be more important but there are cases where the induction is really strong. CF3 and nitro stand out to me as kind of like the two big examples that will overcompensate for that. But both those are relative terms because here we've got a secondary versus a tertiary. You know, if it had been a primary versus a tertiary, hyperconjugation would probably win that first example. So I'm sorry, the world is messy, but I promise not to make it messy on evaluations. And if I do screw it up, both answers will be right. Okay, I think we're going to leave it there for today. What I'm going to try and do this afternoon is post a few more assignments where we start having some of these mechanism problems. The Mobius assignment will go live Thursday at midnight 12:01 a.m. on Thursday. Because that came about really quickly between the last Mobius assignment and this one. The other thing I'm going to post is kind of a better layout of how to submit the SciComm assignment and exactly kind of what I'm expecting for that. So I'll post a PDF on that. I'm also going to post I need to figure out how to submit stuff to drop Blackboard. I just have never done. I'm sure it's not hard, but I just never figured it out. What's going to be covered on this assignment? Everything up to Wednesday's lecture. So everything since the last assignment, mostly as much as I can remember. So I think confirmation, RNS, um, different types of isomers, introduction to mechanism drawing. If you open up there's no corrections, but I think if you open it up, you should be able to see your answers. Nulia, you should be able to access the answers if you try and look at it because the answers are they're like automatically generated because everyone's assignment was different. No two people have the same assignment. Thank you, Nicole. Yeah, I don't quite know how to work that yet. Yeah, so Nulia, it sounds like you need to go under Gray Book, then Details, and you can see the corrections. And again, if something was marked wrong on the assignment, that you look at them, you stare at the answer, you stare at your thing, it's the same thing. Email a screenshot of that to me, and you will get the grade. If you didn't follow the instructions about alphabetical order, or you put random spaces into words, and some of the two words became one word, or one word became two words, I can't help you there because that was kind of the assignment. And I tried to be really clear with the instructions. The final, anyways, I'm going to send out the email on this, but as I think I said last class, is if you do better on a final than the assignment, your assignment mark gets integrated into your final mark. Okay, I will talk to all of you guys on Wednesday. See you then.